Hey guys, we are back with the second installment of this new series, which we haven't figured out what we're going to call it yet. We just got off the phone with Nir Shaviv for the podcast, who is an astrophysicist studying all sorts of crazy stuff. But one of the processes that we ended up discussing was the way that the sun generates its continuous spectrum of emissions, how it gives off all of these beautiful frequencies of light if it's a gas, which is really strange because gases usually give off individual frequencies, not a whole range of them. And so we thought we would just bring in our radioelastic model of the atom and explain why it is that gases give off individual lines, whereas solid bodies, condensed matter, seem to give off continuous spectra.
And why is that, Dr. Delay?
Yeah. Well, I think we have to really start at the beginning with what light is. So we have this model, which you can see a little primer for. We'll post it up here.
It's actually going to be up here, I think.
Up there. And what we're saying is that the radial distribution function for the electron tells us that the electron of an atom can exist out to very far-reaching distances from the nucleus of the atom itself, although most of that charge is usually detected within a very small radius of the nucleus, which we call the electron shell generally.
To put it simply, atoms that are far away from each other are connected by long filamentary strands of the shells.
Exactly. So not only do we use this to explain gravitation as a product of the tension of this connectivity, but we can also think about light as being a conversation that occurs between atoms across this tensioned structure where deformations of that tensioned filament results in photons, essentially. This deformation is actually occurring in waves, and the waves have different character, which we can get into, different polarizations. That's the topic maybe for next week. But as a result of this, the deformations take on a particular quality depending on the location of the atom, whether it's bound up with other atoms or whether it's not.
Less location and more context.
Yeah, context. In fact, gravity and light seem to be largely the result of the nodal context of the atoms. And so what we think is happening in the gas...
Well, okay. So you are dealing with atoms that resonate, and the resonant nature of the surface of this atom as it shifts from discrete energy level to discrete energy level is what's going to give you the color of light that you're talking about. So something that is blue is vibrating at a different frequency than something that is red. Something that is microwave is going to be different from something that is gamma ray.
And as the atom is vibrating like that, it's applying those periodic tensions to the filaments that connect the atoms to one another as well, because they're just extensions of the shell, ultimately.
Which is a key change from the way that people normally look at light as being just these little corpuscles or waves or whatever that are just kind of shot off into dead, empty space. The key innovation of the material model is that the photon, which is the light that you detect, is traveling along a path in between atoms, and it's not just going off into outer space.
Traveling a path within the actual material of the atom itself, which is connecting atoms to one another. And
oh, sorry.
I was just going to say, like, it's sort of a far-out idea because historically, like Anastasia said, the photons are...
Dr. Benderbury, actually.
Dr. Benderbury has said that the photons are treated as if they're flying off from one atom and, who cares about what's happening to it on the other end. We have recently investigated the history of this idea, and going back all the way to the 1920s, you see Gilbert Lewis making the assertion that, wait a second, light can only be considered in the context of two atoms. You always have a detector and an emitter. And a few people over the years have begun really thinking about light as a conversation, particularly Caltech Emeritus Professor Carver Mead, who we had on the podcast, also we'll link that up there, who has done the mathematics to retrace how you can make this event make sense in terms of conversation as opposed to just an emission. So back to the gas.
So in a gas, what's happening is that you have discrete particles. Each molecule is separate from the other molecules. They might interact with some, loose charge based ways like van der Waals interactions or something where things kind of like come together, but that really requires more of a
pressure and
right. So if you just imagine a bunch of atoms that are filling a room and they're not in larger clusters of molecules, they haven't condensed into anything yet, that gas can only vibrate at a specific frequency. Each molecule inside of that gas will only vibrate at a specific frequency, which is why when you're looking at the spectral emission of sodium or phosphorus or nitrogen or any of these things where you take a powder and you put it into a flame and you see what happens in the flame, you see a couple of discrete lines where each of the atomic components of that mixture is vibrating with the added energy of the flame in a very, very discrete way. But that's not what happens in condensed matter. Condensed matter gives you this really beautiful continuous spectrum. It's the rainbow that you see when you reflect a CD, when you reflect the when you diffract the light of the sun in a CD or a crystal or anything else. And what's happening there?
So what we think is happening there, and honestly, what most people would agree is happening, is that the lattice architecture of the material allows for what the mathematicians generally call delocalization of the electron. And I thought that you did a really good job of paraphrasing this idea for Nir Shaviv in our conversation by essentially saying that, okay, these electrons can make very diverse distances of excursion during their electron transitions that allow them to kick off these photons. That's traditionally how it's treated in the mathematical realm description, the classical description of how these lattices participate in the generation of continuous spectra, black body spectra. And I think the main thing that we're trying to clarify here is that when you have a body, if it's even a single atom, it doesn't have very many degrees of freedom by which it can vibrate. However, when you start linking subunits, multiple atoms together, you get all sorts of vibratory modes that can appear in that wider structure as the result of all the subunits. And those overtones, those new ways that the shell can deform and relax, results in the production of a wide range of frequencies of light, that is, deformations of the filaments that are connecting them to the detector system. And that is why gases have lines and condensed matter has a continuous black body spectrum.
See you next time.